So let's take a look at a network or system where the magnetic field is constant, but the area is changing. This is the idea for a railgun. Uh, some people know what that is. We've talked about it a little bit. If you watch YouTube videos on a railgun, they're pretty impressive. And this is the idea. So my magnetic field strength is constant. And what I'm doing is I'm moving this bar in this direction. And I want to know what is my induced potential due to this movement. Well, this vector v, this is the velocity. And so I can write that my differential length and that would be in this direction is going to be equal to my vector times dt. And if we're just going to talk about quantities, then we can write just dx is equal to v dt. And so my differential area is just going to be equal to this length here in between this U section and the rail moving, and that's going to be times dx. And if I substitute my equation, then I'm going to get that the differential area is the length times the velocity times dt. And since it's one loop, I'm just going to look at Faraday's law, and we're not going to worry too much about the negative sign. We're just going to write d phi magnetic field over dt, and that's just going to be equal to the magnetic field times my differential area, because we said the magnetic field was constant, over dt. And if I substitute, and notice that I have dt on the top, dt on the bottom. Those are going to cancel out, and my induced potential is equal to the strength of the magnetic field times the length, or the separation, of these two bars on this U shape times the velocity. Very simple formula for how this bar would move. Now, we can come up with this in a different way. We can come up with it from the force equation. So remember that we had the force of due to a moving charge in a magnetic field is Q times V vector, my velocity, cross B. And if I just take the magnitude, that's the magnitude of the force is QVB. The work that it takes to move that is the force times the length, because I'm moving the charge along this length, and that's just going to be equal to QVB times L, and the potential E is equal to the work divided by the charge, and that just leaves me with BLV. So we came up with this in two different ways. came up with the same answer. So it turns out that if I have a constant magnetic field and I have a bar that I try to move, that there's going to be a force to counteract that. So my force is going to be in this direction. I'll call it force induced, we'll put an I there. And this would be the force mechanical. Now, with a railgun, what they do is they quickly increase the magnetic field, and that increase in magnetic field causes this bar to move to the right. There's a homework assignment problem that talks about this that you'll have to figure out how the relationships between the bar moving and the current and the potential on these rails.